Hi and welcome to the video. In this video we're going to be looking at IP addresses and how we can use those in the network for logical management of the network as it grows and scales out. We make the assumption that we start with a single site and then expand to multiple sites nationally and then perhaps internationally, as well as data centers as well as cloud providers. So having a clear path of IP addressing, very similar to the naming convention, allows us to have a scalable method to manage these networks as they grow. Obviously this is also combined with good documentation, which we'll cover in another video, but predominantly we're going to look at the IP address systems that we can use. To begin with, we need to understand that there are different ranges of networks that we can use. And predominantly this is broken into three main areas. Initially, as we can see on the screen, we have the private network address system, which is what we're going to be focusing on today, which is typically behind the firewall or within the private network. We have the public IP address ranges, which is typically external to the firewall or used for your internet connectivity. And then we also have some special ranges, 127 probably being the most well known, which is a loopback address for these ones just here. Focusing in on the private network addresses, we can see that there's three main areas. There are the Class A, Class B and Class C networks, and this is really defining how large of a scope we can go to. So if we take the Class C network, which is the 192.168.0.0 to 192.168.255.255 address range, that's a Class C, which is a /16 network, and that allows approximately 65,000 IP addresses. As we move up to Class B, we move to 172.16.0.0 to 172.31.255.255, and that's just over 1 million usable IP addresses. And then we move into Class A, which is a /8 network, and that's 10.0.0.0 to 10.255.255.255, and there's 16, almost 17 million usable IP addresses within that one. Within most lab and demo networks, as we say, you can typically get away with the 192.168.0 range. You may not use the whole /16. What you'll see frequently is a /24, which is the range of 254 addresses within a singular octet. So the 192.168.0.0 network as a /24 would be 192.168.0.1 all the way through to 192.168.0.254, and they're the usable addresses on a /24 as an example. Typically you could break down, or you would break down, the larger subnets such as the Class A /8 network to have smaller logical IP address ranges that you can use within the networks, and that's typically how we can go ahead building a scalable network. We're going to use the example to start with. If we have a look at the average home network, what you'll find is on your typical network at home is the PC, laptops, TVs, phones, tablets, maybe a printer, and they'll be connected with a variety of either cables or wirelessly. And if we have a look at your typical home network, that will usually be on the range of 192.168.0.x with a /24 subnet. And that means there's a maximum of 254 usable addresses for that singular range. And we can demonstrate this on the machine that we're on now. If we go ahead and open a command prompt or a PowerShell prompt, we can use the command of ipconfig, and this will demonstrate all of our network connectivity that we have. And as we can see just here, we have a wireless LAN adapter, which I'm using currently, and we're on the 192.168.1 network. The default gateway is a .1 address, and our current IP address is a .241, and we can see the subnet mask of 255.255.255.0, which is a /24 as an alternative way of writing such. As I say, on a home network this is absolutely fine. It's very unlikely you're going to have more than 250 plus devices on that network, so we can get away with using this. When we move into the small office realm, what we'll soon find is that we need to do some segregation. We won't go into how this is done, but typically through VLANs and other methods. But as we move into a small office, we can see here that typically the network looks the same, except we're running some server systems here. We have some PCs and laptops, maybe some phone systems. Still use wireless for the laptops and the mobile phones or smart devices, and then also some printers on the network. But the key added part here is that we have a guest Wi-Fi connection. We won't focus on the security side in this, but as a best practice, it's always good to segregate the client networks out so that any guests that are visiting the site that are not members of the network have their own internet connection if you're going to provide that for them, and that will be segregated from the rest of the network. But we can see in this example here, what we have is the small office using the 192.168.0/24 range, which gives 254 devices on that singular range, and then the guest Wi-Fi using 192.168.10, again /24, 254 addresses. So there's plenty of IP addresses there that are available. And this is fine again for a small office. As we move towards a more medium-sized office, we start to introduce additional technologies, and we might also introduce additional remote working. So if we take a look at the example here, what we've done on the example is we've taken the server network. The data and phones are now separate as well. The internal user wireless is separate. There's also a user VPN access and also the guest Wi-Fi. And we've split these out into the associated ranges. Again, we're using /24s as examples, but you could open these up to be slightly bigger if need be. But for the examples, you can see that as we grow the network out by putting devices on particular address systems, it becomes easier to manage. So we know, for instance, at the moment there is 5 servers on the network. So assuming we start with .1, we know that the first server will be 192.168.10.1, the second is .2, .3, .4, and as we introduce more servers, we just add to that range. Again, each of these /24 networks will give us a maximum of 254 devices. So utilizing that, we know that if we're going to go above that, we can then either increase the subnet mask or add additional ranges. Important part to note here is that when we refer to user VPN, we are referring to the end user connecting directly to the office, not to be mistaken with a site-to-site or mesh, hub and spoke or mesh type VPN. This is purely for users to be able to remote in. So if your core head office has all the servers with all the data, they would log in via their endpoint, whether that be PCs or laptops from home, and that will give them access to this particular part of the network. Moving on from a medium to a large office, what you'll see is that we've done some additional splitting of the resources. And what we've actually done here is we've said, well, we'll run the management as a separate network, the servers as a separate network, the data and phones are now both separated out, the internal wireless, we also have a printers network, the user VPN, so the users can remote into the network still, and also the guest Wi-Fi. You'll also see that we have multiple switches in the center here. Obviously, as the network grows and you add more devices, you'll need more access ports. So we've assumed that there's more switches on the network, which you would have in a larger network. We've also said that there's a couple of access points, and although they'll be broadcasting both the internal and the external wireless, they'll still be centrally controlled via the same IP ranges that we've specified. When we say management, we're looking at the actual management of devices, and this might be a remote management card for a server, such as an ILO or an iDRAC. We might also refer to this for the management ports on the switches and or firewalls or routers if they're separated, and also the management for the wireless access points if there's multiple, whereas the actual servers and the Wi-Fi DHCP scopes or IP addresses that are given to clients are on a separate range so that they are separated from one another. Again, more of a security practice, but we won't focus too much on that in this video. This is purely just how we logically separate the network. Again, we've assumed these are all /24s just for easy management, but again, you could increase these or decrease these as the case may be. And this works fine for small, medium and large offices, and we've just stuck to a very simple 192.168.10.20.30 just for easy thought process and logical management. And we can replicate this out for multiple offices. So what we have here is we have the head office in UK London, and that's using the full range that we've just discussed. We then look at the data center, which is in UK Slough, and we know that we don't need printers or a internal wireless network, so we're only using the networks that we'd need, which is the management, the servers, the data and the user VPN. Perhaps this is a failover site or similar. We then look at the remote office for Manchester. Again, we've effectively replicated all of the address system from our UK head office London, and the same for Los Angeles, Houston and Belfast. This is fine for any cloud-based SaaS applications, so if the sites are never going to talk to each other, this is absolutely fine. Unfortunately, with the networking setup, at some point we're probably going to need to transfer data between sites, or we may have users that visit one site or another, and as a result, they may have data spread across 2 or 3 sites, and they need to be able to talk to each other. Whilst we could introduce user VPNs to all of these sites, there's additional things to think about, such as licensing or costing and scalability. So what we'd probably look to introduce is the site-to-site VPNs, which we can demonstrate just here. Now, as we've said, unfortunately, these are all on the same IP address ranges, which makes site-to-site VPNs increasingly hard. You can do some very fancy natting rules to get around this, but as we scale across from 2, 3, 4, 5, 10, 20, 100 remote sites, it becomes very hard to manage. So we need to think about the IP addressing that we use as we scale this out. As we saw earlier, there's 3 main classes, and if we use the current class that we're using, class C, the 192.168 range, we're limited on the IP address to around 16,000. If we move to a class A, we have around 16, almost 17 million addresses that we can use. The second part we need to think about is whether we want all these addresses to be routable across the VPNs, such as the guest Wi-Fi. From a security standpoint, we don't really need that to be transferable or routable to the rest of the networks across the VPNs, so we can also remove those from the equation. So if we take a quick look at routable and non-routable, we can say, well, the head office in London will have a non-routable guest Wi-Fi, so we won't put that through the VPN, and the same for the other sites here. We could also introduce other non-routable addresses, and that might be for the devices such as IoT devices that are unique to each individual site. There may be some wallboards, displays, etc. And that's really to think about what you need to route and not route across the VPN. Once we know what we are routing and what we aren't routing, we can plan out the IP address ranges. And if we take a look at the example after we've made some changes, we can see that the head office UK in London is now using the 10.0.10, 10.0.20, 10.0.30 ranges as we progress through, and the guest Wi-Fi is on 192.168.250. We can then say that the UK Manchester site is using 10.150.0, 10.150.10, 10.150.20, etc. Again, the guest Wi-Fi is on the 192.168.250, and because these are never going to route to the other sites, we can replicate these IP addresses across all of the sites for the guest Wi-Fi, and there won't be any conflicts. Now, how did we come to this IP address system? We can choose multiple different IP address ranges for different sites, but as we said from the beginning, it's about having a clear plan from the beginning. So as we scale this up, we know what we can use and what's available and not available. If we take a look at the quick worldwide scenario, this is typically the map that I work to when designing out networks, and we can see here that we've split this up into 4 geographical areas, and then also we've called it head office and data centers. So there's 5 areas, if you will. And what we're using is the 10.0 range, because that's the largest scope that we can have, and we're splitting these out logically into different geographical areas, or non-geographical in the case of data centers that may be cloud-based resources. So looking at the top here, we have 10.0.x.x to 10.49.x.x, and we're going to use this for our head office and data centers. We then look at the North American territories, the Latin American territories, EMEA and the APAC regions, and we can see we've used very similar ranges for these different locations. So the North American territories consists of 10.50.x.x to 10.99.x.x. So that gives us the entire range for that geographical region. And we can see that split here with remote offices for Los Angeles and Houston. And we can see that we're using 10.50.0 to 10.50.59 for Los Angeles. And for Houston, we're using 10.50.60 to 10.50.119. We've assumed that there's no sites in Latin America for the moment. In EMEA, we are looking at the remote office for Manchester, which is 10.150.0 all the way through to 10.150.59. And then for the APAC regions, we've got Belfast on the 10.200.0 to 10.200.59. And you'll see there's a slight pattern here as we're using the initial second octets effectively for the location distinguishment. If we take a look at the second page, just here we can see how this is broken down to from a visual point. So we can see that the head offices and the data centers, and this could also be cloud resources as well, as you'll typically pick a region geographically for them to be within. We can see the head office is 10.0.x.x to 10.49.x.x, which gives us an entire range there, multiple different IP address systems that we can use. And then we've also given the data center a very similarly large scope. And there's actually a slight typo. That should be 10.0 to 10.9 for the head office. There we go. And then the data center follows on from 10.10 to 10.19, data center 2, 10.20 to 10.29, all the way through up to 10.40 to 10.49. And that would be our large data centers and our head office, just so we've got plenty of scalable growth. As we look at each of the geographical regions, we can see that we've assigned the North American territories 10.50 to 10.99, and these break down into effectively 4 locations per octet increment. So we have the first 4 sites being 10.50.0 to 10.50.59. That's remote site 1. Remote site 2 would be 10.50.60 to 10.50.119. Remote site 2. Remote site 3 would be 10.50.120 to 10.50.179. And then remote site 4, 10.50.180 to 10.50.239. Remote site 4. Then we move into the next octet. So remote site 5 would consist of 10.51.0 all the way through to 10.51.59. And we repeat this process for each of these for the assigned ranges that we've split up logically. We then do the same for Latin America. As you can see here, we start at 10.10, and the first site will be 10.10.0 to 10.100.0 to 10.100.59, and we repeat this all the way through, and we go all the way through to the last octets, which is 10.149.0 to 10.149.59, all the way through to 10.149.180 to 10.149.239. The same for EMEA and APAC regions. So now we have a rough idea on the IP addresses we can assign to each of the sites, the geographical regions that they apply to, or the data center and cloud regions that they apply to, and then we can look at how we break them down even further for each individual site. So as an example, we're going to take a EMEA range. We're going to choose our remote offices here, and we can see how this is broken down. So remote office 1, 2, 3, and 4 will fall into the 10.150 octet ranges. Remote office 5, 6, 7, and 8 will fall into the 10.151 range, so on and so forth. Effectively, the red highlighted numbers are the changes for the EMEA range, and the last octet in blue is the individual ranges for each scope. Obviously, we've left quite a large amount of ranges between each of these, so if we take the data network as an example, we can see that 10.151.2, which will actually be 20, uses the entire range of 10.151.20 to 10.151.29, so there's multiple usable addresses within that, and we can either open up the /24 scope to increase the number of ranges that we can use, or we can use logical segmentation in each of the buildings that we're working with. So if we take a look at IP addresses with a VLAN ID, we can take a EMEA region, which is 10.150 to 10.199. We'll take a remote office as an example for data, phones, wireless, and printers. So this remote office is on the IP range of 10.151.20 for the data range. The phones are on the 10.151.30 range. The wireless will be on the 10.151.40 range, and the printers on the 10.151.50 range. And we're going to assume that the building that this is located in has floor 0 to floor 4. And you can see here that we've mirrored the address scope to that of the VLAN ID. Again, this is just logical. It isn't needed for each site. You can use any VLAN ID within the usable ranges. But by having a clear segmented logical thought process behind it, for diagnostics, repairs, and scalability, it just becomes easier to work with. So we can take the data range being 10.151.20 for floor 0, and that's a /24. We'll use VLAN 20 for that. And that means any device on that network will be 10.151.20.1234. We can identify that that's floor 0 on VLAN 20. Floor 1 would be 10.151.21 and then 1 to 254 for the scope for them devices. And again, VLAN 21 as the identifier for that octet as well. The same is then true for the phones and the wireless. The exception here would be the printers, which we could effectively, unlikely we're going to have more than a couple of each of these on each floor. So floor 0, we've used the example of 10.151.50.1 and .2 for the two printers on floor 0 or ground floor. Again, we're using VLAN 50 as the identifier because it matches, so it's easy to find. Floor 1 would be .11 and floor 2 would be .21. So we can easily identify that the floor that the device is on, the IP address range it should be on, and if we need to do any diagnostics, we know where it should be able to route through from and to. And this is typically, as I say from the beginning, a high-level principled structure of how I would look to build these networks out. Again, depending on the scenario you're in, you may not need to go to this length, but the key thing to take away here is think about the network you're deploying, think about all the possible network scopes that you may require, whether that be DHCP scopes for endpoint devices or static ranges that you're going to be assigning for servers, printers, management ports, management network devices, etc., and to scale that out accordingly. As we carry on with the videos, we'll be using this exact same IP range to emulate where each of our sites are, and then as we introduce VPNs, remote user VPN, site-to-site VPNs, wireless network devices, we'll start to see how this builds together and how having that logical process there makes it easy to scale out as we continue on. That concludes this video, and in the next video we'll be looking at the actual deployment of our Active Directory domain in the first instance.